All right, in the previous video, we concluded that the cardinality of the set of real numbers is less than the cardinality of the power set of real numbers. And we saw that there are infinitely many different sizes of infinity. So let's look at this for a moment here. The cardinality of the set of natural numbers is smaller than the cardinality of the set of real numbers. We saw that in a previous section. And then in the previous video, we saw that the cardinality set of natural numbers then is also smaller than the cardinality of the power set of natural numbers because the power set is greater. So how do the cardinality of the real numbers and the cardinality of the power set of the natural numbers compare? So is the cardinality of the set of real numbers, the next larger infinity, bigger than the cardinality of the natural numbers? So let's break this down. This infinite set of natural numbers, remember 1, 2, 3, 4, is this less than, right? There's the little tip there, less than. We don't know, but we know that it is definitely less than its own power set, right? The power set. But is there a set in between these two? Right? How do we know that the power set is the next biggest one? We know that the cardinality of the real numbers is larger than the cardinality of the natural numbers. But perhaps there is an infinity between them. How do we order these infinities? Is there a collection of real numbers whose cardinality is strictly greater than the cardinality of natural numbers, yet strictly less than the cardinality of real numbers? Is that possible? Is that impossible? Essentially what we're saying here is, how do we order these infinities? So when we use Cantor's power set theorem, we've seen how to create larger infinities, but how big are these infinities? Are we skipping a whole bunch of infinities in between the ones we are generating? And we know that the cardinality of the real numbers is larger than the cardinality of the natural numbers, but perhaps there's an infinity in between them. Is there a collection of real numbers whose cardinality is strictly greater than the cardinality of the natural numbers? So there's a lot of open questions here, and the continuum hypothesis is a conjecture about this. Unfortunately, this hypothesis is neither true nor false. But here we go. There is no cardinality between the cardinality of the set of natural numbers and the cardinality of the set of real numbers, sometimes referred to as the continuum. There is no size between the size of the natural number set and the real number set. So we don't know if this is true or false, and in fact we can prove that it is not true and it is not false. Think about that for just a moment. So Kurt Gödel in 1940 proved that it's impossible to disprove it. We can't disprove it. But in 1963, Paul Cohen proved that it is impossible to prove it. So that's a lot. Let's kind of come back here and let's look at another paradox. Russell's paradox. Suppose we take every set of every size and simply imagine the set comprising every set. In other words, let's just think of the largest set ever. And it would contain every set as an element, including itself. So this thing is its own power set. This set would be the grandmother of infinities. It would be just everything. Okay, Cantor's power set theorem implies that there is no greatest of all infinities. By this theorem, for any set, the set of all its subsets is strictly bigger. But if we consider this hypothesized biggest set of all sets, we run into a contradiction because it would be impossible for all its subsets to be elements. There's just too many of them. So it cannot contain every set. And the only way around this contradiction is to concede that this huge set is not a set. But we said it was a set, and that exactly is the paradox. The answer here is really tricky. It shows us that the basic sounding idea, it has limitations. The idea that a set is just a bunch of things is not really adequate when we're talking about truly enormous collections. So this paradox forces us to confront the strange fact that some collections are just too unwieldy to call sets. Can we even call them sets anymore? And in fact, this has led to its own complete branch of mathematics called set theory. And that concludes this additional portion of 3.4.